In today's video, we're going to continue to look at the polar coordinate system. Yesterday was mainly an introduction to the polar coordinate system, but we didn't have time yesterday to really delve into why polar coordinates are used, and that's what today is all about. Today, we are going to be describing not individual points in polar coordinates, but rather describing entire graphs and entire shapes using polar coordinates. Because the real benefit of polar coordinates is that they allow you to describe circles and portions of circles very easily. To begin with today, we're going to review what is the graph of an equation. We are going to graph a couple of cool equations in polar coordinates, and then we are going to convert entire equations between the polar coordinate system and the Cartesian coordinate system. A graph is a visual representation of all of the points that satisfy a given equation. For example, what is the graph of the equation y equals 3x? The graph is a visual representation of all the pairs of numbers, one number taking the place of x and another number taking the place of y, that can be plugged into this equation and result in a true statement. For example, if both x and y are equal to 0, and I plug that into the given equation, I get 0 equals 3 times 0, which is true. So 0, 0 would be one solution to the given equation. If I plugged in x equals 1 and y equals 3, then 3 for y and 1 for x would give me the equation 3 equals 3 times 1, which is also true. If I plugged in 2 for x and 6 for y, then that's 6 equals 3 times 2, which is also a true statement, so this is another solution. And likewise, there are many more solutions corresponding to many other potential pairings of x and y. Now, writing down a list of all of these solutions is not practical in terms of time. So instead, we use graphs to visually represent all of the solutions to this equation. We make a note of the solution where x is 0 and y is 0 by plotting the point 0, 0 on this xy plane. We note that x equals 0 and y equals 3 is a solution by plotting the point 1, 3 on the xy plane. And we make a note of the fact that something like -1, -3 was a solution by plotting the point -1, -3 on the xy plane. And so on and so forth. By connecting the dots, we get a visual representation of all the solutions to this equation. Any point on this line represents a pair of numbers, x, y, which, if plugged into this equation, would give you a true statement. Using that same reasoning, we could construct the graph of something like x equals y squared. What are all the pairs of numbers that make this equation true? Well, one possibility, for example, are if x and y are both equal to 0, then x equals 0 and y squared would equal 0, so that would result in a true statement. If x and y are both 1, and I plug in 1 for x and 1 for y, then 1 does equal 1 squared, and this is a true statement. Likewise, if x was 1 and y was -1, 1 is equal to what you get if you square the number -1. So again, we're running out of space and we're running out of patience to manually write down all the x and y pairs that give us a true statement. So to save time and to save space, we represent those solutions visually by plotting the point 0, 0, by plotting the point 1, 1, by plotting the point 1, -1, and connecting the dots. and every location on this graph represents a pair x and y, which makes this equation true. Now sometimes you can figure out the graph of an equation not solely by plotting points, but by also using some other kind of reasoning. For example, someone says, what is the graph of the equation x squared plus y squared equals 9? I could say x squared plus y squared. I've seen that quantity before. In fact, I saw this quantity just yesterday in the formula for conversion between Cartesian coordinates and polar coordinates. X squared plus y squared was equal to r squared. So if I put that information into the given equation, I'm looking for points where r squared is equal to 9. In other words, where r is equal to 3. Now remember, yesterday we defined the polar coordinate r to represent the distance from the origin. So points will be on the graph as long as they are exactly 3 units away from the origin. So let's sketch some points which satisfy the condition that they're 3 units away from the origin. For example, I could go 3 units directly to the right, or I could go 3 units upward, or I could go 3 units to the left, or I could go 3 units downward, or I could go 3 units in any other combination of those directions, for example to the northeast, or any other angle I chose. As a matter of fact, if we considered all possible angles, the number of points which are exactly 3 units away from the origin form in total a circle. So x squared plus y squared equals 9, the equation of a circle of radius 3, the square root of 9. Now this equation in Cartesian coordinates was relatively complicated. X squared plus y squared equals 9. But by converting it to polar coordinates, we got an equation that was much, much simpler. Just r equals 3. And that is the primary benefit of polar coordinates. They give you an extremely simple way to describe circles which are centered at the origin. For example, we could also consider the equation r equals 4. Using similar reasoning to what we used in the previous exercise, r equals 4 would correspond to a circle of radius 4 units, because in this case we can be 4 units away from the origin in any direction. Now primarily, polar coordinates give us a great way to represent the equations of circles which are centered at the origin. R equals number is the circle of radius number centered at 0, 0. Because of how r is defined as a distance as measured from the origin, r equals number is a circle centered at the origin. But on occasion, they can also be a useful way to express circles which are slightly offset from the origin. And that's in this exercise. In this case, we have a circle of radius 3 centered at the location 3, 0. In Cartesian coordinates, the equation of this circle is given by the following. X take away 3. To represent the 3 in the center, x take away 3 quantity squared. Plus y take away nothing. Y take away nothing because we have a 0 for y in the center. Equals 9. This is a particular case of the general equation for a circle that you probably encountered back in Pre-Calc 1. So let me put the little memory bubble over here. The Cartesian equation for a circle with a radius of c and centered at the point where x is a and y is b is given by x minus a squared plus y minus b squared equals radius squared. And so what we're seeing is a very specific case of this general formula from Pre-Calc 1. Now let's see if we can write down a simpler equation for this same circle using polar coordinates. The first thing that I'm going to do is I'm going to try and multiply all of this out. So x minus 3 squared is equal to x squared minus 2 times 3 times x plus 3 squared, which is 9. There's nothing we can do to simplify y squared, and there's nothing that we can do to simplify 9. So now we have x squared plus y squared. We have a negative 6 times x, and we have a plus 9 on both sides. Now the reason that I have specially highlighted the x squared plus y squared is because that entire quantity as a whole can be converted to polar coordinates pretty easily. X squared plus y squared, that entire quantity, could be converted to r squared. Now how would I convert x by itself back into polar coordinates? To convert x by itself, I can use the formula from yesterday that said that the relationship between x and r and theta could be given by the formula x equals r times cosine of theta. This is a great formula if you're converting just an x or just a y, as opposed to converting the entire quantity x squared plus y squared. The entire quantity x squared plus y squared was equal to r squared. However, x by itself can be converted only to r times cosine theta. Now let's do a little bit of cleaning. We have a plus 9 on the left and a plus 9 on the right. So if we subtract that 9 from both sides, we now have r squared minus 6r cos theta equals 0. Next, I can see that both of the terms on the left side contain an r. So I can factor out that r, and I get r multiplied by r minus 6 cosine theta is equal to 0. Now, zero product property tells me that there are two possibilities. R is equal to 0, or r minus 6 cosine theta is equal to 0. But r equals 0 corresponds to starting at the origin and not moving any units away from the origin. So r equals 0 just describes the single point at the origin, 0, 0. Start there and don't move at all. Then you will be located at the origin. Now, we already know that this equation is not just corresponding to a single point at the origin. This equation is an entire circle, radius r, centered at 3, 0. So because this r equals 0 is describing a single point, which is not the circle in this problem, r equals 0 cannot be the correct conversion of the equation to polar coordinates. Instead, the correct conversion to polar coordinates is given by this r minus 6 cosine of theta on the right side. This can be expressed as r equals 6 cosine theta. Not quite as simple as the equation for circles centered at the origin in polar coordinates, but still pretty simple, especially when compared to the Cartesian equation that we started with. So in general, my recommendation when converting equations from Cartesian to polar coordinates is this. First, simplify your Cartesian equation and see if you can find any instances of x squared plus y squared. If you can find an x squared plus y squared, then that entire quantity can be converted to an r squared. Very convenient. Now, aside of that, if there are any remaining isolated x's, then you can convert those individual x's to the quantity r cosine theta. And likewise, any individual y's could be converted to an r sine of theta. From this, you have technically finished converting the equation into polar coordinates. But then it's worth checking to see if your equation can be simplified a little bit through arithmetic, for example, subtracting 9 from both sides, or through some factoring and basic reasoning. For example, here we factored out an r, and we said that r equals 0 corresponds to a single point at the origin, and therefore cannot reasonably describe this circle. Instead, the circle was reasonably described by the equation r equals 6 cosine of theta. And for visual confirmation of the fact that this equation describes the circle in this problem, let's head off to Desmos and let's have a look at the graph. So Desmos is usually pretty good about graphing polar equations. When graphing polar equations, be careful. You need to use the actual letters r and theta if you want to get the true graph. So r would be equal to 6 I said, cosine of, and then I'm going to just type in the word theta, Theta. It'll automatically convert it to the Greek letter theta, and it will recognize that r and theta here are intended to be polar coordinates. And so it's going to create the graph of the equation. It's going to create a graph of all the locations on this graph that make this equation true, where the r is truly equal to 6 times cosine of the angle theta. And we can see, yes, it certainly does form the equation of a circle with its center at the point 3, 0, and with a radius of 3 units. So this is the polar equation of an offset circle. Using Desmos, let's check out the graphs of a few more polar equations. They do get pretty cool from time to time. For example, here we have r is equal to sine of 4 times theta. This one is different from the one before, not just because it has a sign, but also because the number is in a different place. For an offset circle, the constant multiple of 6 was on the output of sine. Let's see what happens when we put the constant multiple on the input of sine. So here is r equals sine of 4 times theta. Would you look at that? This is usually called a polar rose, although I'm not sure if I'm thinking the rose when I look at this particular graph. Maybe some other kind of flower would be more appropriate. The polar rose, if you put a 4 in the input, will end up having 8 2 times 4 leaves on it, or petals I should say. If I change this to 6, now there are a total of 12 petals. 8, there would be 16 petals. Interestingly, the behavior in the petals is different if you have an even constant inside the input versus if you have an odd constant inside the input. If the input has an even number, for example 8, the number of petals is twice as much as the number in the input. But look what happens if I put in 3. If I put 3 in the input, now the number of petals is an exact match to the constant which is in the input. And if I put in 5, likewise, this has 5 petals, 7, 9, and so on. Once again, let's contrast that with what we get if we have a 5 on the outside instead of next to the input. In this case, we get an offset circle. In this case, the circle is offset vertically because we have a sine instead of a cosine. Compare that to the polar rose, which has the constant on the inside, quite a different function. Another graph of a polar equation that's kind of cute that we can look at together is what's called the cardioid. And that is the equation r equals 1 plus cosine of theta. So it's called a cardioid because it's meant to resemble a heart. And so the word heart is related to things like cardiac arrest, for example, coming from a root word meaning heart. However, I personally think that it kind of resembles a lily pad. So this is another kind of cool shape that can be achieved using polar coordinates. It's interesting from time to time just to go in here and play around and see what might happen. For example, instead of having r equals 3 times cosine theta, which is an offset circle of radius 3, what if we did 3 divided by cosine theta? Let's just see what happens. Curiously, we seem to have achieved a vertical line located at x equals 3. Let's just see if we can reason through why this polar equation might have this graph. So if we cleared the fractions by multiplying both sides by cosine theta, then the left side would be r times cosine theta, and the right side would be equal to 3. Now r times cosine theta shows up in one of our conversion formulas between Cartesian and polar coordinates. R times cosine theta is equal to just x. So the polar equation r equals 3 over cosine is equivalent to the Cartesian equation x equals 3. And so that explains why the graph of this particular equation looked like a vertical line through x equals 3. Let's call it there. Today we looked at how to graph equations described in polar coordinates. Polar coordinates provided a particularly convenient way to describe circles and slightly offset circles. Polar coordinates can also be used to describe pretty cool looking graphs such as the cardioid and the polar rose.